So to back up just a little bit, equilibrium is where an isolated system is found with equal probability in each one of its accessible microstates. And um, that is the converse is also true. And we call these microstates, or we total number of microstates, this symbol omega, right? Capital omega. Um, it's really important then I mean, we're introducing a new symbol and to kind of wrap that symbol in a meaning instead of looking at it as something strange, right? So the number of microstates is omega. So if there's a property of a system that has some value x, the number of microstates which have that value x are omega x. So omega x, the total number of microstates with that value x. So then what's the probability of that you're going to have X? Well, the probability you're going to have X is simply the total number of microstates that would have that divided by the total number of microstates. It's actually when you translate it into English, and which you're going to have to do a lot in this chapter, when you translate it in English, it makes much more sense than looking at these new symbols that you haven't assigned meaning to yet. And so that's one of the bits of confusion you're going to run into in some of this class. We're going to be using symbols that have meanings that you don't really attach to them yet. You're pretty much accustomed to calling X position, Y height, Z, these you have meaning you've associated with them, R radius. These are new variables, omega, um, that you're going to have to attach meaning to. And so there's some cognitive work you have to do around that and just sort of keeping in mind, oh yeah, this is one of the things I'm up against. And that's why I provide a white version of the slide decks so that if you want to print it out, you can print it out and you can write notes around that and write notes around what the English meaning of different things are rather than just the mathematics. Thermal equilibrium is one of the things we're going to work towards understanding. And so if you've got these two systems that are adjacent to each other, A and A prime, they can exchange energy. They're isolated from everything else. Again, our box symbology, the double wall out here means they're isolated from everything else. This wall means they can exchange energy. The total number of particles in star is just n plus n prime. So we got A and A prime. Total energy is just U plus U prime. You can exchange energy, but here in this setup, that's all you can exchange. So the probability of finding system A with energy, a particular energy U, right, is going to be the total number of microstates of the system as a whole that have that energy divided by the total number of microstates of the system. Right? Now, the total number of microstates of the system is just a constant, so we can say the probability of this is this constant times the microstates that have U. Um, the total microstates are a product from the two subsystems. So the total number of ways that things can be put together. Think of it this way. If I can put together the A side in 5 different ways, and I can put together the A prime side in 4 different ways. Well, it's not 5 plus 4 because I could have this in one of its ways paired with all the 4 different ways this can be. So it's a multiplier. It's 5 times 4. That would mean 20 different states, not just 5 plus 4. It's 5 times 4. So the total number of microstates at that energy are the microstates in one part of the system at that energy times the microstates in the other side of at that energy. For systems of many particles, increasing the energy dramatically increases the number of microstates. Really brings it up, right? Most probable value of U is where P of U is a maximum. Now this is just a straightforward calculus concept, right? Where it's a maximum, that's the most probable value, and it's proportional to the total number of microstates. when the total number of microstates is a maximum. So let's go do this. We need to find when, so at a maximum, the slope's going to be 0. And so we're going to take the derivative with respect to u to find where the slope is 0. We work through this. We're going to put in u prime is u star minus u. Remember, u prime is a prime's energy. U is A's energy. U star is total energy. So the total number of microstates, now we have it expressed in terms of U star and U, which is great because U star is a constant, right? There's not, back to our diagram, no energy is leaving the system as a whole. U star has to be constant. All right, so what we get from doing this is that the most probable state occurs when the change in the number of microstates in A with respect to energy over the number of microstates is equal to the change in the number of microstates over in A prime with respect to its energies over the number of microstates. All right, so 1 over the number of microstates in system in part A over here times the derivative of that with respect to its energy is 1 over the number of microstates in the other side times the derivative of that over with respect to its energy. And we're just going to define this quantity tau. 1 over tau is 1 over omega d omega du. So since everything else was held fixed, we're actually going to introduce here the fact that this is a partial derivative, right? We weren't letting the number of particles change. We weren't letting the volume change. And that means this is a partial derivative. A partial derivative is really derivative of a function with respect to one variable while holding all other variables constant. We use partial derivatives throughout physics to kind of put together equations and figure out what's going on by looking at it one little piece at a time. So we now have this factor, 1 over tau is 1 over the number of states times the derivative of the number of states, partial derivative of the number of states with respect to the energy, right? Partial derivatives is just another type of derivative. We'll talk about that more as we go along and look in your reading notes to see more on that. So tau and tau prime are equal. So when we're in thermal equilibrium, they're the same. Tau has units of energy, right? This tau has units of energy. And we know two systems in equilibrium have the same temperature. So there's got to be some relationship between tau and temperature. And it turns out there's a proportionality constant between tau and temperature. That is the Boltzmann constant. And so we have our Boltzmann constant in joules per Kelvin, or our Boltzmann constant in electron volts per Kelvin. Remember, 1 electron volt's just 1.6 times 10 to minus 16 joules. So that's how we get to this energy term in terms of the Boltzmann constant. All right, we're going to stop here and pick up in the next part.